Hello, my dear friends. So, today I am going to discuss a problem, and it's just the statement you should hear it once and just boggle your mind up that what is this a question really? So, I just ask you normally that you have a 5 liter of water in a bucket, and by mistake you uh, just toppled the bucket and the water fell out of it. So the water forms a puddle. Puddle is nothing but a big water drop. You can actually approximate it like that. It is a big water drop, and then you have to calculate the area of the puddle, the area of the puddle. So how you will calculate the area of the puddle here? The contact angle is given as 60 degree. So for that to happen, here we should understand one very nice concept. We should talk about surface tension between different boundaries. So first of all, I would like to talk about the shape of the puddle. The shape of the puddle will be such that the sum of the surface energy and the potential energy is minimal. Okay, so whether it will be a paraboloid, hyperboloid, spheroid, anything, it should be such that the energy is minimal at both the water air boundary and the water floor boundary. So first let me show you the water air and the water floor boundary. Suppose if we are talking about this region, so this is the water air boundary tangential to this direction, water air boundary, and this is the water floor boundary. Okay, so first of all, let us see. So the energy per unit area for the water air boundary is surface tension of the water, and we can call it as gamma. Gamma. So gamma is the surface tension of the water at the water air boundary. The second thing, the water has also contact with floor over some particular area. Okay. So the water also has contact with the floor over some particular area. So the gamma here is the surface tension of the water, and the water also has contact with floor over some particular area. So I know that if the area will change, suppose if the area changes, I should know that the contact area between the floor and air will decrease. If the area changes, there is change in energy proportional to the change in area, surface energy density, that will call as gamma dash. So if the area will change, the area of contact between the floor and the water will change, floor and air will change. Suppose if the area increases, the area of the puddle increases, then the area of contact between the floor and air will surely decrease. So first of all, we should know that there is an energy change proportional. Okay, the water has also contact with the floor over some particular area. If the area changes, that we already discussed, there is a change in energy proportional to the change in area, surface energy density, that will call as gamma dash. So here gamma dash and nu, that is the contact angle, surface energy density, and that is proportional to the change in area, the energy proportional to the change in area, and gamma is the energy per unit area, at the water air boundary. Okay, so they characterize the equilibrium at the edge of the body of liquid. So at the edge, here in this portion you can see it. I will just zoom it up a little bit so that we can understand what edge we are talking about. At this edge, we characterize the equilibrium by using the water air boundary, the floor energy density, that is the area that is covered by the puddle, that energy density, and the surface tension. So here between I should say that gamma dash and nu characterize the equilibrium of the body of the at the edge of the body of the liquid. So if the angle of contact line is shifted notionally by s1 from equilibrium position. So what I am just saying that here the contact line, this is the contact line, you can see this is the tangent or the contact line. If this is shifted by s1, if this is shifted to the right by s1, as you can see, I am just shifting it to the right by s1. So this point which was somewhere here earlier will go somewhere there perpendicularly in the direction, this is called s2. And let us say that if this is new, this is also new. By mistake I have written as psi. So this, if this is new, this is also new by simple geometric condition. This is new, 90 minus new and also parallel, both are parallel. So this is new, then this is also new. Okay, so by geometric consideration I will say something afterwards, you should keep that in mind. Then by the principle of virtual work, or you can just say D'Alembert's theorem of virtual work, the sum of the first order changes in surface energies must be zero. Okay, so I already told that this is a prerequisite of learning this concept. So here you can say that along the contact line of unit length, gamma S1 which is W1 and gamma S2 which is W2, uh, it has got unit of joule, is zero. Surface energy density times the distance. So resultant lengthening, what is S2? Resultant lengthening of the water air interface. Water air interface will surely increase by some amount, and that is S2. So from geometry I can say that S2 is equal to S1 cos nu, that from the figure I just told you, that where we considered here you can see that where we considered it as nu, here S2 and S1, all that terms just give us this relation. So here I can just say that gamma dash is minus gamma s gamma cos nu, and in our case this is 60 degrees, so it is minus half gamma, and it is always less than 0. So what is the negative sign? What does it means? Why the negative sign has gives a special resemblance? Here we should understand that negative sign indicates that the water wets the floor. Water wets the floor. For lowering energy, area increases and as large as possible. For water, I know that the contact angle will be less than 90 degree, and for that the area should be as large as possible for lowering the energy or the center of mass of the system wherever it may be located. So the energy is minimal. For lowering energy, area should be maximum. The height of the puddle will decrease, and in that case, we will say that the water will wet the floor. Okay, for some liquid, gamma dash is greater than 90 degree. Example, you can take silver, mercury, that type of liquid. Gamma dash, the energy, the gamma dash here it is negative, but for some liquid it is greater than 0, and the contact angle is greater than 90 degree. So here wetting does not take place, and the tendency to decrease area of contact provides lower energy. So here increasing the area provides lower energy, and here decreasing the area provides lower energy for both gamma. That all depends on gamma dash, the value of gamma dash. Okay, so the gamma dash can be easily written as the energy difference between the two surface density gamma SL, energy per unit area of liquid solid interface, energy per unit area of solid gas interface, not separate roles in themselves. In both of them do not have separate roles, means individually they are not defining something very unique. Okay, so here I can say that surface area of the puddle containing volume V equal to 5 liter of the water and relatively larger AWF is equal to, so here air of the water area of the water air interface, water flow interface must be taken as A because the area is large, and for that approximation I should show you one figure. This figure, as you can see, since the water drop is very large, this area, that curvature area, this curvature area is similar to the floor area because the puddle is very large, relatively large, so the both areas are same. So here if I write the energy, E is equal to gamma A plus gamma dash A plus mg h by 2, that's the potential energy, and here you can say that the center of mass is already at h by 2, so that is the potential energy 2, and here you can say that convert it into gamma 1 minus cos nu A, and since area is height is equal to area upon volume, volume upon area, so volume upon area, that approximation we take here, and following result we get energy as a function of area. Energy as a function of area, here you can say that it is gamma into 1 minus cos nu A plus rho gv square by 2a. So here it can be of the form alpha A plus beta by A. So for the minimum energy we should just differentiate it and equate it to 0. We'll get it A as root of beta upon alpha. So corresponding to E minimum we get the area as rho gv square by 2 into 1 divided by gamma into 1 minus cos nu, and we get this area as 1.8 meter square. And if I calculate the corresponding minimum energy, the calculation will go somewhat like that, and we'll very amazingly we get to know that both of these terms have the same value. So the minimum energy is just 2 times, so the surface energy and the height energy, the potential energy here and the surface energy here, both will give us the same value. So the height of the puddle can also be calculated as V by A and V by rho V square by G, 2 gamma 1 minus cos nu, and then we get 2 gamma by rho G into 1 minus cos nu, and that is approximately 2.7 millimeter. So height of the puddle can also be calculated. And what will happen if there is mercury? Please comment down the video and just tell me what will happen if if I set to calculate the area of the mercury. So the prerequisite was D'Alembert's work theorem, and I hope you like the video. Thanks.